A dipole in a uniform external field refers to a system where two equal and opposite charges are placed in an external electric field that is uniform across the region. Parts. 1. Electric dipole. A dipole consists of two charges, one positive, plus Q, and one negative, Q, separated by a distance. The two charges are equal in magnitude but opposite in sign, and this separation creates a dipole moment. 2. Dipole moment. The dipole moment is a vector quantity that represents the strength and direction of the dipole. It points from the negative charge to the positive charge, and its magnitude depends on the charge and the separation between them. 3. External electric field. A uniform electric field is a field where the field lines are parallel and equally spaced, meaning the electric field strength is the same at all points in the field. This field exerts forces on the dipole. 4. Torque and alignment. When the dipole is placed in the external electric field, the field exerts a torque on the dipole, which tends to rotate it so that the dipole aligns with the direction of the electric field. In this setup, the dipole does not experience any net force, since the forces on the positive and negative charges are equal in magnitude but opposite in direction, but it does experience a torque that tries to orient the dipole with the field. Continuous charge distributions describe situations where electric charge is spread out continuously over a region, rather than being concentrated at discrete points. This spread can happen along a line, over a surface, or throughout a volume. These distributions are important for analyzing real-world charge setups where charges are not just isolated but distributed over a region. Types of continuous charge distributions. 1. Linear charge distribution. Here, the charge is distributed along a one-dimensional line, like a long wire or filament. This means charge exists along the length of the line, and we consider the total charge that is spread over this length. 2. Surface charge distribution. In this case, the charge is spread across a two-dimensional surface. Examples include a charged metal plate or the surface of a conductor. The charge density depends on how the charge is spread out across the surface. 3. Volume charge distribution. This type involves charge spread over a three-dimensional volume, such as inside a charged object. The charge is distributed throughout the entire volume, and the distribution can vary from point to point within the volume. Key points. Total charge. For any of these distributions, the total charge can be calculated by considering how charge is distributed across the length, surface, or volume and summing it up. Electric field. The electric field created by a continuous charge distribution is the result of contributions from each small part of the charge spread across the region. The field depends on how the charge is distributed and the distance from the distribution. Potential. The electric potential at a point due to a continuous charge distribution is also calculated by considering the contributions from all the small pieces of charge that make up the distribution. These distributions help us understand complex scenarios like charged conductors, dielectric materials, and other objects where charge is not just concentrated in one place but spread out across a region. Subscribe our YouTube channel, Learning Cage.